A particle of mass 10 kilograms is described in a circle on a smooth horizontal table. It is connected by a light inelastic string of length 0.5. Inelastic means it can't extend, okay? To a point which is 0.3 meters spherically above the center of the circle. The reaction force of the table is 20 newtons. Find the center of the circle motion, the tension of the string. Find the constant angular velocity omega to one decimal place. If the angular speed is then increased until the particle is on the point of taking off from the table, show that omega equals square root of 24.5. Okay. Okay, so it's on a table. So, and then it's describing circular motion, like so. And circle is connected by light in excess string. Oh, it's above it. Okay. So 0.3 above, yeah?
It says 0.4 above.
Oh, you're right. They changed that question. 0.4. Yeah, it does say 0.4 in the book. So that's, you have the updated version, so they obviously didn't update the online version. Okay, so and it says in the solution it changed that to 0.4. Okay, and then what's this here then, guys? 0.5. And then by Pythagoras' theorem, 345 to 0.3 radius by Pythagoras' theorem. Okay, so now we know that this angle A here, find the radius of the motion, 0.3 meters. Find the tension of the string, not quite there yet. So, see the way it's 0.5, 0.4, 0.3? You can enlarge that by a factor of 10. Doesn't change the shape of the triangle, but it'll make my maths a 3, 4, 5. And it'll still maintain its angle A. Now we know that cos A is 4 over 5, and sin A is 3 over 5. Okay. Now the forces at play are your reaction force R, your weight, which is 10g again, tension, guys, up in this direction here. So, yes.
What's that particle of mass 10 kilos? What is the particle of mass?
A particle of mass 10 kilograms is described in a circle. So it's this one down here. It's on the table.
It's on the circle.
It's described in a circle on a smooth horizontal table. So it's on the table circling, and this point up here is like the point that causes the force. So it's like that's 10 kilograms, and that's your hand moving it around. Okay. So what we have here is what's this? That's T sin A, T cos A. Are we happy with that? T sin A, T cos A? Okie dokie. So, T sin A, T cos A. So, T cos A being 4 over 5t, T sin A being 3 over 5t. We're going to choose, find the tension in the string. Okay. So, what goes up equals what goes down. It tells us the reaction force, doesn't it? 20N. So R equals 20N. So, forces up versus forces down. What's going up? R is going up, yeah? R is otherwise known as 20. What else is going up? Anything else causing it to stay up? 4 over 5t. And then equals force down. What? Sorry? 10g. And now we can find the tension straight away here. 4 over 5t equals 10g is 98, by the way. 98 minus 20. 4 over 5t equals 78. bring over the 5 and the 4, so t equals 78 divided by 5 over 4. Oh, sorry, not divided by, sorry, I get that wrong. It's multiplied by 5 over 4. Or divided by 4 over 5, so 75 multiplied by 5 divided by 4. What do you get for the tension?
97.5.
97.5?
Yeah.
Okay, thank you. Okay, 97.5 newtons. Okay. Now, find the constant angular velocity to one decimal place. Fc equals m/r omega squared. What's Fc, guys? What's forcing it to go into the middle of its circle? Your 3/5 of t. Your 3/5 of t is what's causing it to circle in its motion. Okay, so 3/5 of t. Your mass is 10. Your radius is 0.3, and your angular momentum, you haven't got a clue about it. Okay, guys, so it's going to be 3/5 of t multiplied by 97.5. All of that is going to be divided by 10 times 0.3. What you get? And then you got to square root the answer. So 3/5 of 97, just call it out when you get it. Divided by 10 times 0.3, which is 3. Root the answer. I got 4.41. What's anybody else get? And is it 4.41? Okay, let's go with 4.4 radians per second. Okay, so W equals 4.4 rad per second. Now, it states another problem now. The next problem is you're just going to keep increasing the speed until the particle is on the point of taking off the table. Now, when you're on the point of taking off the table, what happens is that's the table, that's the particle. That's when you're firmly on the table. Just when you're at the point of taking off the table. This can be like a nanometer. This can be like the smallest distance possible. And imagine that we have a massive zoom. You're just ever so slightly off the table. Just at that brief millisecond, microsecond, wherever it is, you're just at the brink and you're just lifted that tiny amount. The minute you lift that tiny amount, what happens to the reaction force R? What happens to R? It's non-existent, equals 0. So all you gotta do is go back to your old work, and all what you gotta do is just rub out the R, the presence of the R. Just didn't exist, never existed. To 20, and then what's 98 multiplied by 5 divided by 4? It's increasing the amount of tension now because it's all going through the tension. It's not being supported by the table. So what's 98 multiplied by 5 divided by 4? What did you say? 100 and?
22.5.
Alright, 122.5. Okay, go back down to your old maths here. Remember we did 3/5 of t? It's still 3/5 of t, except however the t this time isn't 97.5. It is 122.5. Okay, so now we're going to put all this in our calculator and we want to prove that it's the square root of 24.5. So 3/5 of 122.5, and then divide that by 3, square root of 24.5. Okay. A particle of mass m kilograms is connected by means of a light inaccessible string of length L meters at fixed point O. O is the fixed point, M is the moving particle. String of length L. The particle is described as a horizontal circle with angular speed w rad per second. The centre of the circle is a distance h below O. Draw a clear diagram showing all the forces acting on the particle. Okay, so what we're going to do is we're going to make a quick diagram here, like so. We know that's angle theta. We know this is length L. We know that's height h. Call this x for a minute. L squared equals x squared plus h squared. Oh, that's alright, yeah. And then x squared equals L squared minus h squared. X equals the square root of L squared minus h squared. So, it's a standard Pythagoras theorem. And now we know what that is there. Now, this in turn will mean that cos theta is h over L, nothing too fancy about that. Sin theta, however, is going to be the square root of L squared minus h squared all over L. Okay, now that's done. We're going to resolve our forces. Force that acts up here, guys, is tension, right? So what we can do is we can draw a diagram of tension. The tension going up this way here. So T, that's theta. So that's going to be T cos theta, T sin theta. Okay? So T sin theta going this direction here, T cos theta going upwards. Okay? What else do we have in the diagram? We're going to have our mg coming down. Show that h equals gw squared. Show that h equals gw squared. There's no reason why this question should be any different from our other questions. The only difference is it hasn't given us any numbers, but the theory is still the same. Forces up equals forces down. Do you notice that there's no angle in here? There's no sign of theta whatsoever. Yeah, would everybody agree with that? No sign of theta whatsoever. It means that we obviously substituted in cos theta and sin theta along the line and got rid of theta. It's gone. So we obviously, that's one of our crucial steps here, is to get rid of that system. Okay, so forces up, guys. T cos theta equals force down mg. Cos theta is h over L. Th over L. Th over L equals mg. Like in previous questions, we're going to isolate T. T equals L mg all over h. Okay. Next part then is centripetal acceleration. Fc equals mr omega squared. Chose mr omega squared purely because of the presence of the omega squared. If that was a phi squared in that formula, I would have chosen mv squared over r. But it's really specifying that once the omega. So, what we're going to do this time, Fc is what, guys? T sin theta. T sin theta equals mr omega squared. There's actually nothing I can do there. Do we know what r is? We got that earlier, didn't we? The radius is square root of L squared minus h squared. So the root L squared minus H squared is R. So it's going to be square root of L squared minus H squared, and then multiply by omega squared. Sine theta, guys. Sine theta is root L squared minus H squared all over L. That equals m omega squared, and this is root L squared minus H squared. So what about the L squared minus H squared, guys? Cancel them off there. And now we're going to find out that t on its own, bring up the L, is L m omega squared. Now these two formulas can now be compared to each other, where Lmg over h equals Lm omega squared. M's will cancel, L's will cancel, and we'll have omega squared, what we're looking to get on its own, h. Did I leave out a h? No, it's still there. So bring up the h and bring down the omega squared. H equals g over omega squared. Prove. If the horizontal circle must remain at least 0.25 meters below 0, or below the point O, calculate correct to one decimal place the maximum value of omega. Okay, so h, its height below, the h value is your value directly below your point O, this value here. So what we're going to say is that it has to be above, h has to be greater than or equal to 0.25. Everybody agree with that? Therefore, g over omega squared has to be greater than 0.25. And therefore, what we're going to do? We're going to do g divided by 0.25 greater than equal to omega squared. Omega squared greater than equal to g over 0.25. Summary square root 9.8 divided by a quarter. 9.8 divided by a quarter. Square root the answer. 6.26. So let's call it. Oh, I also did one thing I forgot to. You need a minimum speed, not a maximum speed, because the more you spin it, the greater its height. So remember, when you spin an object around, when you start first spinning the hammer throw, it lies below your waist height. The faster you turn, the higher it gets. So to keep a weighted object above a certain height, we need to keep it below a minimum speed, not below a maximum speed. So it's going to be above. What do we say? 6.2 or 6.3? Round up 6.3. I'll round it off. Okay. 6.3 rads per second. Good with that?